Hi everyone, my name is Steven. I'm currently a PhD student at Columbia University, and in this talk I'll be presenting CSafe, an intelligent audio wearable platform for improving construction worker safety in urban environments. Motor vehicle accidents are the leading cause of work-related deaths in the United States. In 2018, out of the 5,250 worker fatalities, 2,080 of them were from motor vehicles, a large portion of them in construction working. Additionally, since 2009, there has been a 50% increase in pedestrian and pedestrian worker-related deaths, with 2019 being the highest it's ever been in 30 years. So this is a growing concern. To help reduce the number of worker-related accidents, we propose CSafe, a low-cost end-to-end audio-based wearable system that detects and localizes vehicles and alerts workers in noisy construction site scenarios. CSafe consists of an embedded wearable platform with an array of microphones interfacing with an acoustic embedded front end that is all integrated into a common construction helmet wearable. The system uses a novel adaptive filtering architecture that iteratively filters out construction sounds over time and improves vehicle detection. And CSafe also provides audio, haptic, and visual alerts to the worker. Now, this is a significantly more challenging problem than previous works in the area. So previously, we proposed an acoustic headset-based wearable for improving pedestrian safety. The system had high vehicle detection and localization accuracy. It was affordable and it was practical, meaning it was low latency and it lasted for a long time. We initially tried to apply this system to construction worker safety, but due to the noisy environments of construction sites where there could be tools that are orders of magnitude greater than that of vehicles, we found that our localization and detection modules were performing much worse. Because you can imagine with all these loud noises, it can be very difficult to even hear a vehicle passing by. This challenge alone requires us to completely overhaul our system architecture and algorithms. To address this challenge, we take an acoustic filtering approach where by filtering out construction sounds, we improve vehicle detection and localization. Now, acoustic filtering, there's two broad categories of work: multi-channel methods and single-channel or content-based methods. So multi-channel methods such as adaptive filtering and beamforming uses multiple microphones in space to typically enhance signals coming from a specific direction. And single-channel methods such as dictionary learning and neural networks leverage learned models or prior knowledge of specific sounds that are soon present in the environment to filter them out. Now, both have strengths and weaknesses. Multi-channel methods, you typically need to know the location of the source beforehand, so you require a localization module. And if, for instance, a vehicle and a construction sound were coming from the same direction, enhancing in that direction, you may not be able to get an SNR or detection improvement. Single channel methods don't really suffer from this, but you're always assuming that what you're filtering and have a model for is present, which isn't always the case in a continuous system, so you require some sort of activity detector to turn on or off the filtering. Additionally, many of these methods, such as deep neural networks, have a very labor-intensive training process, and they're only trained to account for one specific type of sound, commonly speech. So if we wanted to incorporate other sounds later on, it may be very inflexible or difficult to do if we were to just take advantage of this. So in light of this, we propose the CSafe noise adaptive filtering architecture, which intelligently leverages both spatial and content-based filtering in an adaptive feedback architecture to iteratively over time improve construction sound filtering. CSafe, the adaptive filtering architecture, is easily configurable to new sounds. We also allow workers to supply their own snippets of their own construction sounds of their own construction site to improve filtering. So here's the CSafe noise adaptive filtering architecture. We first sample a channel of audio from our array, and we apply our content-based filters to filter out construction sounds. that we learned from previous iterations. So I'll get to this in a little bit. But afterwards, we perform localization to determine the significant sources in the environment, which then spatial filtering uses these locations to further refine our signals. And from here, we get our clean source signals and source locations, which then can be analyzed later down the pipeline for vehicles. In this architecture, next we use our library of construction sounds to detect if any of the signals still have construction sounds. And if they do, we update our content filters to filter them out. So I'll first start off with localization. Most multi-source localization algorithms follow a similar pipeline where our signals are in the frequency domain and we look at each frequency. We assume that if a sound is coming from a specific direction, there is an expected phase difference that you see between the different microphones depending on the physical configuration. And we then can compare this expected phase difference with what we actually observe to generate a probability distribution that a signal at a frequency is coming at a specific direction. And then we aggregate these frequencies across every frequency, and then we can then determine that we get this aggregate distribution where the locations are determined to be wherever the peaks are. Now, it turns out generating these distributions per frequency is very computationally expensive. So we adopt an approach that simplifies this, assigning each frequency to just one direction, the most likely direction. So now that we have our source locations, we can perform spatial filtering. And to do this, we use a filter bank of static filters generated with a Gaussian confined window that is centered at whatever direction that the source is localized to with an adjustable beam width. The idea being that whatever signal aligns with the localized direction will be retained and all signals that are misaligned will be attenuated. And we use a static filter bank because we can pre-compute these filter banks in advance, which would reduce runtime computation. And then we get our clean signal sources. Next, we analyze our signal sources using a noise detector and our library of construction sound models to see if any of them are present. And if they are present, we update our filters to then filter them out in the next iterations. To filter them out, we propose a novel single channel or content-based filtering method called probabilistic template matching that uses learned templates, which I'll get into what that means in a little bit, of construction sounds in order to filter them out. So this method is also lightweight and it allows us to incorporate new sounds into the filtering pipeline very easily, and it allows us to incorporate snippets that users or workers can provide of their own construction site to improve filtering. So for the noise detection module, we model every single noise as a Gaussian mixture model. And the idea is if our source signal, our observation falls within a certain threshold of any one of these Gaussians, then we detect noise and we use the corresponding Gaussian as a template to filter out the construction noise. So this template is being used in our probabilistic template matching algorithm coming up next, but in a sense, this links our detection module with filtering with our noise module, such that they're all mutually benefiting from each other. So using our template, we perform probabilistic template matching. So for PTM, our signal that we want to filter is assumed to be in the frequency domain. We look at the magnitude vector, and the goal is to estimate a set of filter coefficients lambda such that when you apply it to our non-filter signal, we obtain a filter signal Z such that the probability that our filter signal is a construction sound C is as small as possible. And here we model that construction sound probability as the Gaussian template that we just established. But if we're to optimize based off of a Gaussian, all of our coefficients will go to 0 due to the nature of Gaussians, and this would mean all our sound gets eliminated. So to prevent this from happening, we introduce a novel constraint where we limit the divergence or the difference between the filtered signal and the non-filtered signal by a certain threshold, which then would mean we don't eliminate every single sound from the environment. And then we can obtain our update equations using gradient descent methods and Lagrange multipliers. And using this architecture, we observe that after just a few seconds of running, we're able to eliminate most of the construction sounds from the environment. So now I'll go ahead and introduce the full CSafe system architecture with the embedded hardware platform consisting of an array of 4 microphones, which then get fed into a Cortex M4, which performs sampling and FFT feature extraction. These features are sent over to the smartphone platform, where our CSafe noise filtering pipeline cleans the signal, and we run machine learning classifiers for vehicle detection. We borrow our machine learning vehicle detector from our pedestrian safety work. We process windows in 250 milliseconds with 50% overlap. In order to run in real time, we would need to sample 1/2 of this window and perform all our computation within 250 milliseconds. We accomplish this in 236 milliseconds, which means we can run in real time. And additionally, this platform can run off of 2 AAA batteries for 14.5 hours, which is well above a typical workday. To perform performance evaluation, we divided this into 2 categories. The adaptive filtering architecture evaluation, where we compare CSafe against existing filtering methods to see which provides a better boost in detection performance, and the real-world system evaluation, where we evaluate CSafe against existing state-of-the-art safety platforms. For the filtering architecture evaluation, we generated a training data set consisting of a collection of common construction sounds and vehicle sounds, and we use this to train our filtering architecture along with our filtering algorithms that we compared against. And for testing, we constructed a construction site data set where we went to a real construction site and we recorded sounds from a 4 microphone circular array, passing vehicles, construction sounds, and mixtures, all of which were mixed in the real world, none of it being artificial, as is done in many filtering or source separation works. We evaluate against CSafe personal and generic, 2 modes of operation for CSafe. So the personalized version is where the user records the noise from their environment and we build a model off of that, whereas CSafe generic, we use the pre-built models to perform filtering. And we evaluate against 4 different configurations. A MM-dense LSTM, a neural network-based filtering algorithm, a dictionary learning-based filtering algorithm, and a spatial filtering adaptive beamforming algorithm, as well as just feeding in the raw audio. And here is the vehicle detection performance. We see CSafe has the highest true positive rate, meaning it detects more windows where vehicles are present than any other method, and it detected every single vehicle that passed, whereas all the other methods missed about 25% of the vehicles. For the real-world evaluation, we evaluated CSafe against our pause pedestrian safety work, where we had a user wear each of these systems at a real construction site. So here are the vehicle detection performance metrics. We see both CSafe systems performing better than pause, and they're able to detect most vehicles passing by, whereas pause missed almost a third of the vehicles. For localization, we see that CSafe personalized and generic also perform better because they're able to filter out the construction sound, whereas pause most of the time localizes the construction sound rather than the passing vehicle. All right, in conclusion, we introduced CSafe, a low-cost wearable platform for improving construction worker safety. And to accomplish this, we introduced the CSafe adaptive filtering architecture to filter out construction sounds over time and improve vehicle detection and localization. We evaluated CSafe against existing filtering algorithms and audio safety platforms to show improvements in vehicle detection and localization in real construction sites. So thank you for this opportunity to share our work.